Okay. In the second part, I'd like to give you more details about the stimulus timing design. But before that, I have to again mention the BOLD signal properties. And in this slide, I'd like to give you a new term right here. It's called the HRF. It actually represents the hemodynamic response function. This is actually the BOLD signal that we are anticipated to see when there is a single neural activity right here. So you can see right here, actually the neuronal firing and the postsynaptic potential occur very soon. We have already mentioned that it's actually in the range between tens to hundreds milliseconds. But because the nature of the vascular response is not that quick, the smooth muscle reaction is not that quick. So actually, there is a time delay. There is a time delay actually around 1 to 2 seconds. And in this case, sometimes we will give an initial dip right here. Sometimes you can see the dotted right here. It is called initial undershoot or initial dip. But in some kind of the HRF, we will ignore this kind of the situation. We will just give a rising up curve right here, but ignore the initial dip. So it depends on the function, what kind of the HR function that you are using. But in this case, actually we use the solid line right here. So we will ignore this initial dip. Okay, but still there is a 1 to 2 second delay right here. So once the neural activity happens, it takes a 1 second delay right here. Then the vascular response will showing up. That means the BOLD signal will start to increase. And around 4 to 6 seconds after the neural activity, it will reach a peak value right here. Around 5 to 6, I think. 4 is a little bit too short. So around 5 to 6 seconds right here. In this case, you can see the peak value is located at the, I think, the 6 seconds after the neural activity. And it takes around 20 seconds to have actually the recovery or the signal profile, the BOLD signal profile come back to the baseline situation. So this will take around 20 to 30 seconds. Depends on the activation. Actually, it can differ between brain regions even within one subject. For example, the prefrontal lobe may have different HRF compared to the occipital lobe. It may be different. So we say there may have the inter-region difference even within one subject. And also between subjects, or we say inter-subject difference may also exist. For example, the younger subject and the elder subject, they may have different vascular response for sure. Okay. So that's why normally when we design a study, we will have a so-called control group. And normally this control group, we don't want the age or gender difference is too significant, because it may definitely insert some difference, essential difference, but you claim that brain activation is actually induced by the task, but not the subjects per se. But actually, this is not true. Okay. And sometimes we can also use some adaptations of HRF. Here, this one is the original waveform for the HRF. Okay. But we can also calculate the temporal derivative right here, this one, temporal derivative right here. And this one can be used to indicate the onset time, actually. And also you can, again, use this one to do another derivative. We call this one is the dispersion derivative. This one, dispersion derivative, this one. This can actually give you another information. But actually, use the very first one is fine. If you are going to use the second one or third one, that is because you want to probe some other physiological phenomenon behind the fMRI. But most of the time, use the first one is pretty okay. But you can see there are two different derivatives from the original one. Okay. Regarding the stimulus timing design, actually there are two main designs that you should learn. The first one is the so-called block design. Actually, this is a very famous one. Actually, I think over 80% of the fMRI study use this kind of design, block design. And another one is so-called event-related design. This is actually the famous design, not for fMRI, but actually for EEG or MEG. When you really want to investigate a single event, then you will use the event-related design, ER. Okay. So when we are talking about the block design, actually we will combine the BOLD response to a number of continuous trials, or you can say number of continuous stimuli. So we will repeatedly give the stimuli. For example, we ask the participant to do the hand grasping repeatedly during a specific time period right here. Okay, and this is kind of the block design. But for event-related design, actually we'd like to obtain the BOLD response to a single event. That means I only ask the subject to do one single hand grasping, just one time, and I like to see the BOLD response related to this single event. And I may wait for maybe another 20 seconds. Then I ask the subject to do again the one single time hand grasping. Then I'd like to see again whether there is a BOLD response corresponding to this kind of single event. Okay. So actually these two are very different design, and they have their own pros and cons. I will introduce this later. But I think you should know another point right here, that normally when we are talking about an experimental design, we also care about the efficiency. Efficiency means that the more efficient a design is, actually the less scan time is needed to achieve sufficient power. When I say power, that is a detection power or a statistical power that I can claim the BOLD response is really correlated to condition or to the stimuli. Okay, so you definitely don't want to deliver, the 2 hour fMRI study, because your subject will complain all the time. But if you want to shorten the scan time, or maybe shorten to maybe 20 minutes, you still need to make sure that the detection power is sufficient. It's still sufficient to give the inference for your study. Okay. So now when we say efficiency, it's actually the trade-off between scan time and the detection power. So just keep this point in mind. Okay. I try to illustrate the different types of the design. The first one is a block design. So first of all, you need to take the triangle as the single trial right here, or a single event, or a single stimulus right here. So for the red one is one type, for example, the right hand grasping. And another one, yellow one, may represent the left hand grasping. Okay, just another kind of stimulus. So as you can see right here, the block design, that means I will intensively ask the subject to do the hand grasping in a continuous period right here. So for example, within these 10 seconds, the subjects are asked to do maybe 8 hand grasping continuously. And for the following 8 seconds, the subjects are asked to be relaxed, fully relaxed. Don't move, and just relax your hand. And then for another 8 seconds, now this is another condition for the left hand grasping. Okay, for another 10 seconds, then resting, then right hand grasping. So this is called block design. We aim to deliver the stimuli continuously to enhance the BOLD response. Actually, for the slow event-related, ER represent the event-related. For the slow event-related design, actually, we will simply deliver one single stimulus for a time. So you can see right here, just right hand, one single grasping for the right hand. And we will wait for another 10 to 20 seconds. Then the subject is asked to perform the left hand grasping. Okay, and again, left hand, right hand, left hand, right hand. As you can see right here, why we put the slow right here? Because most of the time, subject is doing nothing. Just relax, just doing nothing. So actually, over the same time, scanning time, actually, in this case, you already ask a subject to do maybe 24 hand grasping. But for this case, only maybe 6 hand grasping. It's pretty slow. Actually, most of the time, you are simply waiting for the BOLD recovery to the baseline. It's actually pretty time-consuming in this case. So there is a modified version right here. We call rapid ER version, rapid ER design right here. So you can see right here, we try to occupy the resting period right here using different kinds of condition. Of course, we won't continue to use the same one, because if we use the same time right here, it's more like the block design. So actually we try to alternatively put the condition in this timeline right here. So now right hand, left, right, and you can see they are actually slightly different between the time interval right here. Sometimes it's longer, sometimes it's shorter, and now a little bit longer. It's pretty longer right here. You try to modulate, try to change the time interval between conditions or between the stimuli. Okay, so this is so-called rapid ER design. Don't worry about the detail. I'll tell you the detail later. But now you just use this kind of timeline, this figure, to understand what's the essential difference between these design. And finally, there is a so-called mixed design. Actually, it looks like the block design, but actually in this block, there are different right and left within one block. So this kind of mixed design. So it's more like a design that combine the pros from ER and block design. But actually, this is more complex one to deliver your stimuli. So this is one maybe a little advanced one. If you are the beginner for the fMRI, I will encourage you to learn this one very first in the very beginning part, and then you can go into the rapid ER version right here, and then finally go to the mixed design. Okay. So we start from the block design. So actually, we say that we will give the continuous stimuli within a time period, and normally this time period will last for I think it can be as short as 10 seconds. Okay, 10 seconds to as long as the 20 or 30 seconds right here. This is a number copied from a textbook, but anyway, just 10 to 30 seconds is the number range that we use to build a block. So now when I say block, that means this continuous period, and we will ask the subject to do the resting or to do the task. Okay. So there are 3 points you should learn. The first one is if you have multiple conditions, for example, left hand grasping and right hand grasping, please make sure that the number of scans should be equal in all conditions. So if you have 3 blocks for left hand, you definitely need 3 blocks for right hand. You cannot just put the unequal blocks for different conditions. That will cause some variance, essential variance for this condition. Not necessarily from the brain activation, but because the experimental design. So just remember that the number of scans should be equal in all conditions. And the second, remember that we normally don't use a very, very long block, because longer blocks will cause the interference from a low frequency noise. What is the low frequency noise? That normally is the some kind of signal driven, or sometimes we call it the signal shifting. This kind of the low frequency noise may, I may say mix it into the BOLD signal. If you use a very long, for example, 40 or 50 second block, that means you may have a high possibility to actually mix the low frequency noise into your BOLD signal. So normally we will use, I think the common number is around 20 seconds. Okay. The final one is, please remember that not only the low frequency noise may mix into your signal if you use longer blocks, but also the strength of the brain signal can decrease over time. If you ask the subject to do the hand grasping for 2 seconds, that definitely will saturate or give some fatigue state to the subject's brain, because you just ask the brain continues to do the same thing. So the brain signal or the BOLD signal will actually decrease over time. You won't anticipate a plateau right here. It actually will decrease over time if the block is too long. Okay, so I think the 20 seconds is a normal range that we use. Don't use too long or too short. Okay.
When you say 20 seconds,
yeah,
one grasp takes 20 seconds?
No. The block. So within a block, you can ask the subject to do the grasp in maybe 1 second frequency, just do the hand grasping, but it can repeat for 20 seconds. So if there is a 1 second frequency right here, and then it's 20 grasping within a block. Okay. But of course, normally we don't simply give a fixed. When I say fixed, that means it is nothing different compared to the very previous second. For example, if you want to display an image and a picture, but the picture lasts for 20 seconds and doesn't make any difference, then it become actually not a stimulus because you are getting used to this picture. So at the very beginning, it is a stimulus, but for the maybe 3 or 4 seconds after, it's just a fixed picture right here. It make no stimulus after all. So actually you need to consider about during the block. Normally we will give the several different stimulus. For example, the unback. Unback is one of the study that we will continuously display different numbers on the screen. We will always ask the subject to compare the current numbers with the previous 1 or 2 to check whether the number is the same or not. If the same, press the button. If not, do nothing. And you will give several, for example, maybe 30 different numbers. Each one may only display for 500 milliseconds, 0.5 second. So you can have 20 to 30 different numbers on the screen during this maybe 20-second block. Okay. So continuous stimuli is the essential point for the block design, not a fixed one. Okay. And when we are talking about the block design, you need to learn this function we call the boxcar function. Actually, it just look like this one, just like the square profile right here, but we call boxcar. So it changes with time, but it's more like several boxes right here. Okay. So this one, when you see the line, see that maybe the value of 0, that means this is in the maybe resting or control period right here. And once the value comes to 1 or another value greater than 0, then that means this is the task period. For example, the hand grasping or something. So resting, hand grasping, resting, hand grasping, and so forth, so on. Okay. And now you can see this is the study design. This is the original block design. However, our brain won't act like a machine. So not simply turn on and turn off. We need to consider the HRF. Remember the hemodynamic response function, HRF. So actually, we will anticipate the actual BOLD signal will more look like this one. Okay, not the boxcar, but we will use this boxcar to confound with the HRF. So it will look more like this one. So you will have an overshoot right here and undershoot right here. And the change is not a sudden change right here. It's a gradual change from 0, gradually change to the maybe over 1, then come back to 1. And then when the task is over, gradually change back to the maybe under 0 and then come back to 0. So this is a more realistic one that is similar to the BOLD signal. Okay, so just memorize that BOLD changes, this is a wrong word, do not suddenly activate or stop in the way modeled by the boxcar function. So we will actually use the B figure is the realistic one that we'd like to see in the BOLD profile. Okay, so here is some illustration for the some term. For example, the overshoot right here, and here is the undershoot. Okay, you just enlarge. I just try to enlarge one task right here. So you can see this is more like the gradual change during this period, not a very sharp edge right here. Okay. Yeah. function 它到底是要做什么用？概念上来说，你总是要先告诉你要分析的这一个程式说 ，OK， 我总是要预期什么时候会有事件的发生。对，所以这个东西你还是必须要给，但是你总是要去跟我们刚刚说 hemodynamic response function 去做一个整合了。你不能就用它，因为我们身体不是这么快的开关嘛。所以这个是一个我们透过数学上的 convolution， 你可以把 HRF 跟 boxcar function 得到这样的一个综合结果。但是你还是会背上这个 boxcar function 嘛，因为你总是要知道什么 period 是在做事情，什么时候是没有。所以这个 boxcar function 你总是要先画出来，再去跟 HRF 作用，得到一个这个比较 anticipated 的一个这个 BOLD signal 样貌。OK。
那秀右边黑色这样图是有？
这个是 enlarge， 我把其中一段。
哦。
对对对，所以你就看到说，这个 overshoot 是长这个样子。所以因为这个其实有点窄了，就看起来有点陡，其实它是缓慢上去的。啊，就是我们说这个缓慢应该还记得吧？应该其实是 take 4 to 6 seconds， 从没有到达到 peak 应该是4 to 6 seconds， 这个 original idea 应该是不变的。OK。So what are the pros or the advantages of block design? Actually, it definitely has a high detection power of activation region because we accumulate stimuli into a short period. So it definitely can increase the detection power or statistical power for identifying the activation region. Okay. And the second, this is actually the most widely used approach or most common one for fMRI study. I believe over 80 or 90% studies are using the block design. So this is definitely the one, or maybe the only one that you should learn when you start figure out how fMRI works. Okay. And the final one is the accurate estimation of HRF function is not that important. As I mentioned before, that actually HRF may be a little bit different between brain regions and between subjects. But actually, when you're considering about the block design, the accurate HRF profile is not that important because the HRF actually will accumulate into some kind of a part2 or some kind of a box profile right here. So this is not solely depends on a single profile. So even you have a slightly different in HRF, it doesn't actually cause a very huge bias for the analysis result. Okay, so this is three very important points and why people always use the block design for most of the study. If I'd like to answer the question, which is the key region, and if I want to actually write a program or just programming our code, this is the most easy way to do. And the final one, we don't need to consider the difference of the HRM for several different conditions. So what is the cons? What is the disadvantages of the block designs? First, if your key question is to differentiate the temporal profile, for different conditions, then block design cannot do so because we accumulate the BOLD response for several different stimuli. So if you want to decipher or differentiate the single event BOLD profile, it is not going to happen. Okay, so it's a poor estimation power for a single event or to differentiate the different conditions. It's very hard to do so. Okay, and again, it's actually very predictable for a subject. Even I ask a subject to do the several stimuli within a block, actually the subject will get used to it. I'll start to, okay, I don't need to think anything. I just repeatedly do the same thing. So it will become very predictable. And as we know that if the study is very predictable, it will actually reduce the brain activation. It's kind of the phenomenon that you can observe in our brain. And the third one is pretty similar to the first one. We cannot look at the effects, the BOLD effects of the single event. Okay. And finally, if you have so many conditions, for example, not simply the right hand grasping, left hand grasping, you may have maybe left ankle dorsiflexion, right ankle dorsiflexion. If you have 4 conditions, then when you're using the block design, the scan time will be very, very long. That is what we said unmanageable. The scan time is too long because we have 4 conditions, and each condition may need at least 3 to 5 blocks, and you need to consider the baseline or resting interval. Then the scan time may become very, very long, around 20 or 30 minutes, simply for this fMRI study. So this is the situation that you need to consider. If you have so many different conditions, block design may not be a proper way to do so. And the next one is so-called event-related design, but we will start from the slow version right here. Okay, so we can see actually we can again try to figure out what is the anticipated BOLD signal would be. We will start from the neuronal activity right here. Actually, as we mentioned, that the neuronal activity is pretty short. Actually, for a single event, it will only last for tens or hundreds of milliseconds. So it's more like a very short peak right here. Very short peak right here. Okay. But now we will use the convolution. This is the symbol for the convolution operator right here. We will convolve the neuronal activity with the hemodynamic function. It's a little bit different because you cannot see the undershoot right here. It's a little bit different. Okay. But now if you convolve this hemodynamic function with the neuronal activity, now you will get the anticipated BOLD signal will be this one. So this is not a very short peak right here. It's actually become a wider one right here. Okay. So for every single neuronal activity, you will anticipate to see that the BOLD signal will look like this one. So if you have a sufficient long time interval between two neuronal activities, you will see the full BOLD signal profile right here. And this BOLD signal profile will be pretty similar with the hemodynamic function right here. So actually, this is a way that if you are eager to find out or identify the hemodynamic response function, slow event-related design can definitely help you to do so. Okay. And we say if you want to use a slow version to recover the hemodynamic function, the optimal or recommended interval, we say inter-trial interval. That means from this trial to another one. This is the inter-trial interval. I would say it is recommended to be around 12 seconds. Or maybe longer, because if you give longer time, you will definitely ensure that the BOLD signal can go back to the baseline. Will have a full recovery. So if you use a shorter one, then the BOLD signal may overlap with each other. Then it will definitely make it more difficult to recover or to reconstruct a hemodynamic response function. Okay. Of course, for a longer stimuli, this period means that for each stimulus, the time interval, for example, 2 seconds, that means the stimulus displayed on the screen. For example, the instruction displayed for shorter than 2 seconds, then 12-second interval is good. But if your stimulus is longer, for example, you display the instruction for longer than 2 seconds, then you definitely need a longer interval for this short event-related design. Okay. So what is the pros for the what is a good thing for the slow event-related design? Definitely, if you are really interested in single event-induced BOLD signal change, you can use this one. It has excellent estimation of the BOLD changes, and it's definitely useful for studies with delayed periods right there. So this is why we call slow, because it allows the BOLD signal has a full recovery right there. And also, it is very useful when you think that there is a motion artifact, because you have a sufficient time interval to tease out the artifact. So this is another advantage for the slow event-related designs. However, the cons is greater, much more greater than pros actually, because it has a very poor detection power, because you can only allow very, very few trials within a certain interval, a certain scan time. For example, 10 minutes, you may only have maybe 10 or 20 trials. Compared to block design, it's a very, very few number right there. So the detection power becomes very, very low. And also, most of the subject may just fall asleep during the scan, because it's very, very bored. Maybe only 10% of the scan time the subject needs to do something, but 90% all they need to do is relax, and relax that means very easy to get fall into sleep. Okay. So how about making it fast? Can we give a faster version of the event-related design? Of course, but before I introduce so-called rapid ER version, we need to first review the linearity of the BOLD signal right here. Linearity is actually the phenomenon that we always ask that, do things add up? Do the BOLD signal, BOLD response add up with each other? We take this as an example. When you see a block right here, that means we give one stimulus right here. And here is another stimulus, here is another one. So we have 3 stimulus right here. If each one can induce a BOLD response, for the very first one, you can see this is a one trial response right here. Okay? And for the second one, actually, it's pretty close with each other. So the BOLD response will add up with each other. Actually, it's pretty like the it's pretty like the block design. Okay, so you can see the second one will become larger than the single stimulus right here. If you have two stimuli right here, you will observe the both signal growing larger right here. And for the third one, again, it's growing larger. Of course, there definitely has a limitation right here. It definitely will reach a saturation position right here. But for this case, only three stimuli, it didn't reach the saturation state. So you can see actually they are pretty good at linearity for these three stimuli right here. How can we say that there is a good linearity? You can do the subtraction. For example, here is the first BOLD response right here. I can use the second curve. I mean, if you have two stimuli right here, you can use this second profile. You can use this one to minus the first one. So you will acquire this curve. If you use the second curve minus the first one, you will get a red one right here. And again, you can use the third one, the third curve, to minus the second one. So again, you can get a green one right here. Okay, so you can see that actually the three profile is similar with each other, not really identical with each other, but actually similar with each other. If you again rearrange the time points, you just put the red curve and the green curve again with the very first time point right here. You can see actually these three curves is pretty similar with each other. So I would say that not quite linear, but good enough. Not identical one, but pretty similar with each other. So we would say linearity may exist in BOLD response, but there is a specific requirement right here. Actually, we would say normally if you want a very good linearity showing up, the ITI, the inter-trial interval, we would recommend that at least 4 seconds. Don't put the trial or the stimulus too close to each other. At least a 4-second ITI is recommended. And also, it depends on the neurons that you are deal with. Actually, there are two different types of the response. First one we call tonic receptors. That means if you have continuous, it's more like a block design. You have a continuous stimuli right here. Actually, each vertical line represents the neural activity right here. You can see the several different neural activities right here. However, the interval will growing longer and longer. Okay, but if you are dealing with the fast receptors, that means it will become actually just rapidly adapt to the continuous stimuli, and this will turn off the neural activity right here. So in this kind of a receptor, actually, you cannot anticipate that there is any linearity in this kind of situation because the neural activity will very quick turn off, turn down after the continuous stimuli right here. But in this situation, yes, you can say the linearity may exist because the continuous neural activity will be induced with this kind of the continuous stimuli. Okay. So you can see even you can drive up the several different neural activity, the strength or the activity strength will actually reduce. The first one will be the most strongest one, but the following one will gradually reduce for several milliseconds. Okay, so I think this is a basic idea. Just that BOLD has general linearity, but it isn't totally linear. But I think this property is good enough that we can use so-called the rapid version of the ER because things do add up. Not that linear, but good enough. Okay. So for the rapid ER version right here, actually, we now try to shorten the ITI, the inter-trial interval right here. As you can see right here, different color represent different conditions or different stimuli right here. You can see now we don't really actually wait for a very, very long period. We now put the events pretty close with each other. However, the interval may be a random profile. We not always put the ITI in a fixed value. Actually, you can see the pink one and the yellow one is pretty close right here. But this one, the pink one and the yellow one is pretty far from each other. So we try to give a random interval between each other. And sometimes you can see this is a single event. This is a single event. However, this is a double event compared to the single event. Sometimes it's pretty far, sometimes it's pretty close. We will put the whole design in a very random way. However, we will ensure that we will get one event, two event, and triple event equally. So now we can do the subtraction with each other. Now we can recover what is the single BOLD signal for the yellow event or for the pink event. Okay, this is some mystery behind this kind of a design. Okay, so you can actually put every single BOLD signal for each event. If they are close to each other, they will become closer right here. And now you can just add up all the events right here. For example, you can add up the pink one. So this is a pink profile for the pink events right here. Okay, and this one maybe the yellow one. And this is the overall combined BOLD signal right here. So the BOLD signal become very, very complex right here. But if you can if you can really have the original design on hand, you can actually reconstruct every single BOLD signal right here. Okay. However, this one is definitely the advanced study design. I won't recommend you, the beginner like you guys, to do the rapid ER design. Definitely, you need a very good skill for programming, and also you need to be very careful when you think about the whole scenario about the stimuli. Okay, and another thing is that when you're doing the rapid ER design, you need to ensure that there is no significant anti-correlation. What is the anti-correlation? That means all the yellow and the pink event just show up alternatively. That means you can anticipate if there is no yellow, then there is pink. That means a very high anti-correlation between each other. And normally, when we are going to use a GLM, I will introduce in maybe a couple weeks later. When we use the general linear model right here, it will always fail if your design has a very strong anti-correlation between two conditions. So for the jitter version, that means we will try to give various time interval between these two conditions. So the profile becomes very complex. It's kind of the random process that we put into the design. And also you can see the BOLD signal changes will become larger if you give larger interval between two conditions right here. Okay, so I think this is so-called rapid and jitter. Jitter means we put this kind of phenomenon, this kind of design into the ER version. Okay, so this is a rapid and a jitter version. So it can guarantee that we can actually use the laser or shorter scanning time, but it has a very good estimation power. So we say this is a high detection power, and it can put in an predictable order. This is very important because we say predictable will reduce the brain activation. So now we can put in a very unpredictable order. And definitely subjects don't get so bored. So I think subjects will become very happy after they come outside the scanning room. So what is the comps? Actually, compared to the block design, the detection power is not that strong. Block design is the highest one. The approach has the highest detection power. And also, we need a very strong assumption about the linearity. So the ITI should not be lesser than 4 seconds. But if it's really lesser than 4 seconds, you need to keep in mind non-linearity will show up. Okay. And finally, the errors of the HRF model may cause a very wrong result when you do the inference. So you need to watch out this point. So I think I in the final two slides, I think I just put the profile right here. Here is the anticipated BOLD signal right here for the block design. This is more like a general way you can see. And for the event-related one is more random one that you can see right here. Okay, so final slide, I'm going to give you a summary of the experimental design. I think each one has its pros and cons, but I try to list the pros for each design. So every single time if you try to use different design, you can keep this in mind. If you want to have a very strong detection power, then you use block design. And also we say if you want to estimate the state changes, it's very useful when you use the block design. Event-related design, if you care about the time course of the BOLD signal, specifically for the event-related response, then you use the event-related design. And definitely use the rapid version because it can give a very good detection power and also very good estimation power. But definitely it may need very complicated programming skill that you need to deliver your presentation in such elegant way. Okay. However, there is a final one I didn't mention in this course, but I think if you'd like to read more, you can find some materials online. There is a mixed design. Definitely it can combine both pros from different designs, but of course, not only the presentation will be delivered in a very complicated way, also the analysis will become very complicated because it combines these two different designs. So I think today I try to go through the essential ideas about the experimental design of fMRI. I hope you can get the general analogy about this. So maybe next time if you are reading some articles or literatures, you can somehow understand why they are going to use this kind of design. Okay. So again, today's course you can download from my website, and also the online video will be uploaded by the end of the weekend. Okay.